Okay, so here we go. So problem number 10 from, what do we got, chapter 12? All right, so the figure looks like this. You've got a ceiling with these weights hanging from it. This guy is A, which has a weight of 40 newtons. Over here, we've got B, which has got a weight of 50 newtons. You know what, let's do this. Let's just call this FA. And we'll call this FB, so we don't have two FGs hanging out on our drawing. Okay, let's see, and then they give you a couple angles. So they tell us that this angle here is 35 degrees, and long story short, we're trying to find this angle over here, right? Good? All right, so, they also give us three different tensions. So, tension 1, tension 2, tension 3. All right, so this is, you absolutely have to know how to do these types of problems. Torque isn't really an issue here because there are no rigid bodies that are being caused to rotate, right? Because everything's string, you know? But the idea is, at each of these junctures, here specifically, and here, we have to have a net force of 0. So that tells me, so if I focus on this point, let's call this point P, as in point. I can write a simple equation that will allow me to find T1. Yeah, the idea is, look, the vertical component of T1 has to be supporting this mass, right? Does that make sense? Okay, so that means that if I've got T1 here, T1 vertical has got to be 40 newtons, right? And if this is 35 degrees, then I can do a little bit of trig and find T1. Good? So that turns out to be 49 newtons if you figure it out. Good? All right, well, I might as well finish the triangle. I can do a little bit of trig and find this component over here, and if you do that, it turns out to be 28 newtons. Good? So what that means is I've got, from T1 that I drew there, I've got, it's pulling this way with 28 newtons, and it's pulling this way with 40 newtons. So my vertical forces have to cancel. So what does tension 2 have to be? 28 newtons, right? Because our tension from tension 1 is pulling this way with 28 newtons, but it's not moving that way. So tension 2 must also be 28 newtons. Follow? Oh, well, that means because this rope is, uniform, it's not moving, that means the tension at this end needs to be 28 newtons, which means now the horizontal component of T3 is 28 newtons. So now I can go over here, let's draw tension 3. So here's tension 3. Horizontal component has got to be 28 newtons. And what does the vertical component have to be? Vertical component's got to be 50. And now I can find, wrong angle. Pretend that's not there. I can find my theta, right? Do you guys agree that this theta is the same as that one? Because they're alternate interior angles. Good?
Yeah, I was checking.
Yeah, there isn't. No, I don't think there is a way to, no, there's no way to solve that before. Questions, you guys?
How would you know that's not? Like, how do you know it's not? Other than the fact that you just solved that, how would you figure out when you're like?
Because it says the system in the figure is in equilibrium.
How would anything ever like be slanted instead of like parallel to the floor? Ever be slanted?
Could tension 2 be slanted? Is that what you're asking?
Yeah.
Sure. Yeah, and I mean, that would add an extra layer of difficulty, because then you'd have to deal with the components of tension too. And I think then we would need some more information to solve it. But yeah, I mean, sure, there's no magic reason why that middle rope T2 has to be horizontal. Good. Good. Yeah.
Oh, I was gonna ask you.
Everybody good with that? Okay, what do you got?
22.
22? Problem? 22?
Yeah.
Oh, the rock climber one? Oh, which reminds me, I need to mark Kurt absent. He told me he doesn't like me, so I'm not coming anymore. Okay, 22. I like this question. All right, so let me see if I can draw this thing. So we got a wall, we got another wall, we got our dude. That'll do. All right, and let's see. It gives us some information. It tells us that his center of mass is here, and that the distance between this wall and the center of mass is d. It tells us the width of the gap is w, and it tells us that the distance between his hands and his feet is h. All right, now, I haven't read the problem yet, but let's kind of think about what's going on here. All right? So the idea is, with his hands, which way is he pulling the wall? I guess it's got to be kind of odd. He's pulling this way, right? Right? So that means that there's a force from the wall pushing this hand this way, right? Does that make sense? And there's friction there. So that friction force is either pulling up or down. You can make a pretty safe guess as for which way that friction's probably acting. Right? The friction is probably pulling up, right? So does the problem give that a name, I guess, before I start jumping in here? It says the coefficient of static friction between his hands and the rock is mu1. So let's call this friction 1. So force of friction 1 is going to be up. Does that make sense? All right. Now remember, he's not moving at all. So the net torque needs to be 0. So if for a minute we consider this the pivot point, then what other forces are acting on it? Well, gravity is pulling him down, creating a torque that would rotate him counterclockwise, right? Follow? So there needs to be something else creating a torque clockwise, right? So over here at his feet, the wall is pushing his foot this way. So here's the force of wall 2. Call this force of wall 1. And again, there's another friction force, right? So I think that's your drawing of your object with all of the forces on it. And I made some assumptions there. We might find out that we're wrong in one of the directions of those friction forces, maybe, but I don't think so. All right, are we good? All right. Here, David. Here, have a pen. Okay. I got it. All right. Okay. Let's see. So what else do we know? We know his mass. We know that this width here is 0.2 meters. We know that this distance is 0.40 meters. We know these coefficients of friction. So the coefficient over here on this side is 0.4, very small coefficient of friction. But the coefficient of friction on this side is 1.2. All right. So question A says, what's the least horizontal pull by the hands and push by the feet that will keep the climber stable? Wow. So, thoughts? Well, yeah. So the only two horizontal forces I see are, these two horizontal forces. So yeah, I agree. Those two ought to be equal, right? Okay, so that means I don't even need to distinguish between 1 and 2. How so?
Because I guess like the way he's holding up the two things, he's sort of
Yeah, exactly. That's why they tell you that this center of mass is over here. They're showing you that around any pivot point you pick, it's going to cause rotation counterclockwise. Good. All right. So let's see if we can come up with some relationships here. And I always like to start with my net force stuff first. It doesn't always lead anywhere, but it's sort of the easiest, right? Because with your net torque equation, it depends on the choice of your pivot point, right? But with force, that's not the case. So here are the things that I know. I know these two forces have to be equal. So I'm going to write down something dumb here, but oops, I was trying to switch colors there. So those two forces of the walls have to be equal. All right. So that's horizontal. Tell me something about the vertical forces. Sure. Yeah, they got all cancel out mg, right? So I'm looking at this and I'm thinking, all right, well, that means that force of friction 1 plus force of friction 2 plus, well, I guess minus mg, right? Has got to equal 0, right? We're going to do something really cool. Are you guys ready for this? Check it out. Force of friction 1. Force of friction is coefficient of friction times normal force, right? Okay, so this is going to be 0.4 times, what do I use for my normal force? Force of the wall. Plus, this force of friction is its coefficient of friction, 1.2 times the other force of the wall, but they're the same. Oh, neat. And that's got to equal mg if you move the mg to the other side, right? Follow?
What's the one subtract?
They're in opposite direction. So the two frictional forces are up. Mg is down, so I was just kind of thinking of it as being a negative force. Maybe this statement is easier, just to say that these two upward forces have to cancel this one downward force. However you want to think of that. All right, everybody good with this? All right, so what happens here, you guys? Yeah, you go. 1.6 times the force of the wall has got to equal mg. So that's 55 times 9.8. And solve it. And the force of the wall turns out to be whatever I said it was on the sheet. 340 newtons. And I don't think it's exact. I think it's, something, and then I round it off to sig digs. All right. So, that's everything. Except, so now I know my force of the wall. You can certainly find these forces of friction, right? Good. So I guess we should probably do that. So let's see. So 340 times 0.4, that's going to be 680. So I'm looking at 136 up here. And this one's going to be whatever 1.2 times that is. So 340 plus 68 is 408. Can anybody confirm those for me? Is that right? Okay, cool. Okay. All right. So now let's see. So that was part A. Part B. For the horizontal pole from part A, what must be the vertical distance? So we got to find h. So now what should I be thinking about? I heard somebody say it. Rotational, right? I need to now think about my net torque, right? So I got to pick a pivot point, and honestly, we know all of our forces, so it sort of doesn't matter what pivot point you pick. Okay? So let me do this. So this one's 340. This one's 340. And then let me do this. Cool. All right, so let's find our net torque. What do we want to pick as a pivot point? There's two good choices. Yeah, either pick this as your pivot point, so then the distance will be here, right? Or pick this as your pivot point, and then your distance is up here, right? Cool? All right, so here's an instance where I think it's really important that instead of setting one torque equal to another torque that you write an expression that says total torque equals 0. Okay? So here's our idea. Net torque has got to be 0. So our net torque is, well, let's see, it's the torque from gravity plus the torque from friction 1 plus the torque from wall 1 plus the torque from friction 2 plus the torque from wall 2. Now, some of those are going to be 0, but I'm just being thorough to make a point. Right? Because there's 5 forces, right? 2 here, and gravity. Yeah.
Are your wall forces not being canceled out by the force of the person?
How do you mean?
Because like you're pulling on it, and that's like canceling out the wall. Or you're pushing on the wall, so that's like...
I guess I'm not understanding what you're asking. So,
You're putting a force on the wall when you pull it.
correct. But that's a force on the wall, not a force on you.
Okay, so you don't include it in your...
I see. Yes, correct. So, yeah. So what we're interested in is not what the wall does, and I don't mean that to sound snarky. We're interested in what the rock climber dude does. So all I care about are the forces on the climber. And all of the forces in this cluttered drawing here are forces on the climber. So yeah, the idea is, yeah, the climber's totally pulling the wall with 340 newtons, but that means the wall's pushing him with 340 newtons, and that's the force ultimately that I care about. Does that make sense? Everybody? That's a big idea. Like capital B, big idea. Good? All right. Cool. So let's do this. So our net torque has got to be 0. All right, torque from gravity. So here's the operative thing with torque, you guys. We want force times d sine theta. In other words, force times the component of the radius that's perpendicular to that force. So here's my force of gravity. Do I use this as my radius, this weird distance here? What do I use? The distance from the wall, because that's what's perpendicular to this force, right? From this pivot point, right? Cool? And again, if I didn't make it clear, this is my chosen pivot point, the big green dot, where his hands are. So maybe I should put a little net torque around H for where his hands are. Cool? All right, so we're going to have our torque from gravity is going to be 55 times 9.8 times 0.4. And then you need to decide, let's see, positive, right? Or counterclockwise, positive, right? All right. Plus torque from friction 1. What is it, you guys? 0, because my distance is 0. Torque from wall 1. Also 0. Plus torque from friction 2. Well, that's 408 newtons, right? Times what distance, you guys? 0.6, 0.4, 0.8, 0.2. Where's the pivot point, you guys? Yep, it's just 0.2, right? Because this force is upwards, so I want to know horizontally how far is the force from my chosen pivot point. So it's just 0.2. All right, let's see. Positive or negative? Yeah, clockwise. Oh, that's kind of weird, isn't it? Right? It's both the friction and his weight are rotating him this way, right? So our last torque is the force of the wall, 340 newtons times H. Right? Because the force is this way, and I want to know the vertical distance down to that force. All right, and then finally, that torque to me looks like it's going to be negative, right? Because it's going to make him rotate clockwise, I just overheard somebody say. So I guess you could put in a negative sign here and then solve for H. Cool, you guys? Any problems? That's a neat problem. There's a lot going on there. That's horizontal and vertical forces, it's torque. It's a really good example of how your choice of pivot points simplifies problems, right? So we didn't need to worry about these two torques.
Would that be like
How hard would that be like for
No.
I
I'll be honest with you. I haven't seen a ton of these types of problems in FRQs. They show up in multiple choicey questions, but they're significantly shorter. Okay, and in retrospect, wish I had downsized this section a little bit. The emphasis on the test is not the chapter 12 stuff. It's definitely the chapter 11 stuff. Okay, I mean, there is some of this, but I think it's a little more predictable. And like, if you can do this, then you're gold. You know what I mean? So I don't think this was time poorly spent. Like, this is a good problem. Cool. All right, part C and D ask about if the coefficient of friction was less. So how would that have affected, where is it? How would that have affected this calculation? Smaller coefficient of friction at either end would have meant you need a bigger force from the wall, right? Cool. So does that answer the question or no? What happens to the answer A? Gets bigger. What happens to the answer from B? Ooh. So the force from the wall gets bigger. How's that going to affect our H? My knee-jerk reaction is... That coefficient of friction would affect this and this equally, but wouldn't affect that. Would it? No, it would not. To be honest, I'd have to go back and do a quick sample calculation, or solve it generically with mu instead of mu1 and mu2. Let me see what I wrote in my notes. What's that? Yeah, I know. What is this number? What number was that, you guys? 22. Thanks. Oh, what did I write? Nothing. Okay, so let's think about it. Did anybody come up with anything? What do you guys think? So, if these coefficients of friction are smaller, you're still going to have to account for just as much torque here. I think that the height would have to be bigger. I'm 99% sure on that. Because you still have to account for this. A smaller coefficient of friction will decrease this, but this still needs to account for this, which hasn't changed. So, does that jive or no?
Doesn't it increase the force?
Oh, right. Oh, it increases the force, right. And it would increase your friction. Ugh. There's no way it can be smaller. Crap. You know, I don't know, and I don't want to spend time on it right now because that's, you know, you certainly wouldn't need to know anything like that for the test tomorrow. So I'll sit down and see if I can figure it out, but don't worry about it. No. All right. What else do we need to look at? Things that jump out at me as being important problems, you guys. I don't know if this helps any. You definitely need to be able to solve those like ladder problems. I don't remember if I put one on the test, but I've seen them over all kinds of AP tests. That would be like a good, multiple choice on an AP test problem. So like multiple choice 14 and 15 are good ones to make sure you understand. There's a problem one with a ladder. Number 7, the one about the window cleaner on the ladder. 39, I just heard somebody say, another ladder one. So stuff like that. Yeah. So to me, those are good. 37 is another good one. That's actually 37 is very similar to the example I did in class. I don't know. What do you guys got? Other stuff? 39? 739. I'm worried that's actually a little bit on the harder side. There's a lot of forces to keep track of there. When I said the ladder ones, I was thinking a single ladder against a wall. That's a step ladder. There's a lot going on there. Let me take a look and see how long the solution for that one is and if it's worthwhile or if that's biting off more than we want to mess with for the test. Oh no, please. Well, it's a bunch of geometry, but the math on it isn't hard. Yeah, let's do that one. We can do that. It's not bad. I saw one just like this I was looking through Mr. Brunner's old quests. I saw this in one of the quests, so he must have thought it was important too, so, for what it's worth. Okay, so we've got a stepladder, and this man who is strangely standing with his arms crossed defiantly. I will not hold on. Screw you, safety. I think that joke was funnier than it got credit for. Oh, that's unstable equilibrium right there. You guys are just grumpy today. All right. There. Okay. So let's see. What do we know? So we know sides A, C, and AE are each 2.4 meters long. So that's 2.44. Who writes these problems? So that's 2.44 meters. Similarly on the other side. It's hinged at C. Yes. Bar BD is a tie rod that's 0.762 meters long. It's halfway up, so that means that this distance is going to be 1.22. A man weighing 854 newtons climbs 1.8 meters up the ladder. So 1.8 meters, and he weighs, force of man equals 854 newtons. This actually, now the more I think about it, is a great problem to do because you can greatly simplify it. All right, so that's our setup. Does it tell us the mass of the ladder? Yes, neglecting the mass of the ladder. So we got to find the tension in the tie rod. So we're assuming it's like like a light aluminum ladder or something like that. So we got to do two things. We got to find the tension in this tie rod, and we got to find the magnitude of the forces on the ladder from the floor at A and E. All right. So you guys ready for the super secret ninja trick?
Yes.
So when you solve this, so I looked at the book solution, and the book finds this tension first, and it's a pain in the can. All right. The easier way to do it is this. Think about the ladder as a whole. Okay? There are only three forces on the ladder as a whole. There's a normal force here, there's a normal force here, and this, right? Plus, there may be some frictional forces, maybe. But my guess is that the tie rod is holding this together, and so the frictional forces are going to be a non-issue. Cool? Now, and even if there are frictional forces here, we'll figure that out in a minute. What I'm about to show you doesn't matter. Okay, so is everybody okay with my crappy drawing? All right, so check it out. What I'm going to do, let's call this force 1, and we'll call this force 2. So there's two unknown forces. Do you guys agree I could pretty easily find this distance? Right? In fact, if this is halfway up, doesn't that mean that this should just be double this? Right? Because similar triangles, right? So this ought to be whatever 0.762 times 2 is. So what is that, 1.524? I did that in my head, is that right? Anybody? That's fine. Oh, look at my notes then. Yeah, 1.524. Okay, cool. All right, so let's consider the net torque around one of these points. So let's consider the net torque around that point. So the net torque around that point is the torque produced by force 1, the torque produced by the man, plus the torque produced by support 2. Okay, well, the torque from force 1 is what? 0, right? Plus the torque from the man. Well, let's see. That force is 854 newtons. Times, you got to do a little bit of geometry and find this horizontal distance. Okay, but you can certainly do that by doing a similar triangle, where you would do 2.4 is to 0.762 as 1.8 is to x. It's just ratios. Or you can find the angle and do some trig. Follow or no? Do I need to go through how I'm about to get that number? A lot of you are shaking your head. Okay, so that turns out to be, oh shoot, 0.2? Will that be right? Oh shoot, I think I chose the other point as my pivot point when I did. Oh, here it is, 0.562. There it is. So that 0.562, if you're keeping track, is this little distance here, 0.562. Good? All right, let's see. Clockwise or counterclockwise? That's clockwise, so that's going to be a negative torque, right? Plus the torque from this thing. Well, that's F2 times 1.524. Does that make sense, you guys? If it helps any of you guys, this is exactly the same thing as if it had just been a beam with support 1, support 2, and a dude standing, you know, however far over he was. Does that make sense? The fact that it's tall doesn't affect anything. Make sense? Okay. Oh, all right. So solve this, and your F2 turns out to be, well, it's on the sheet, right? I called it F normal at point E, so that's 315 newtons. And so now finding F1 is super easy. Why? Your net force has got to be 0. So these two forces have to cancel out his weight. So 315 subtracted from 854 means F1 has got to be 539. There you go. There's the two forces at the supports. Make sense? All right. Now to find the tension in the rod, well, let's see. We want to break this up into chunks. So what I would do is, my drawing's totally getting cluttered. Consider this length of the board. Right? There's only two forces on it. There's this normal force producing torque and this tie rod producing torque. Does that make sense? So figure out this distance. It's what, 0.762? So F2 times 0.762 equals tension in the tie rod times whatever this vertical distance is. And you're done. Make sense or no? So that's a problem that when you first look at it, it's seemingly very, very complicated. But if you kind of break it up into little bits, it's not horrible. Cool? Okay. All right. I feel like you guys are not up to speed on stuff. Let me kind of, all of these multiple choice questions are important. Otherwise I wouldn't. I've been trying to be pretty selective with the problems I pick, sometimes more successfully than others. But what's that? 15 on the multiple choice, sure. Oh, the letter. Yeah, so this is kind of just a, well, never mind, I'll show it. Here we go. 15, an 80 Newton uniform plank leans against a frictionless wall as shown. So, tells you this distance here is 3 meters, this distance here is 4 meters. What's the 80 newtons, you guys? mg, right? So, oh, damn it, I just gave away. All right, why did I put it there? Center mass, right? Okay, so it wants to know the torque applied about point P by the wall. Oh, and the wall is frictionless too, so that means that the only force is going to be a normal force from the wall, right? Cool. So, the net torque about this point has to be 0, right? Well, there's only two forces providing torque. there's the torque from gravity and the torque from the wall. And those two torques have to equal each other, right? So I'll write sloppily, the torque from the wall has got to equal the torque from gravity. So let's deal with the torque from gravity first. That's going to be the force of gravity, 80 newtons, times, what should I use for my distance there, you guys? Yeah, 1.5, right? Because if this is halfway up, then it's also halfway across, right? Because they're just similar triangles, right? Oh, and that's got to equal the torque from the wall, and that's what we were trying to find. So it's 120 newton meters. I'm surprised it didn't ask you for the force of the wall, but maybe I'm getting ahead of myself. Mickey, are you good up to there? So what would the force from the wall be, you guys? 30, right? Because it's got a distance of 4, and the torque has got to be 120. Cool? Mickey, you good?
Yeah.
So, yes, capital B, important. I just said capital B, important. Important doesn't start with a B.
Should there be friction from the floor keeping the spike up or
Ooh,
sliding?
there 100% has to be friction. So we decided that this force had to be 30 newtons, right? So that means that at this point, two things are happening. I'm glad you asked this question. So there's got to be friction. We already know how much. 30 newtons, right? Because our net force horizontally has got to be 0. So if the wall's pushing this way with 30 newtons, then we've got to have a frictional force of 30 newtons this way to cancel that 30 newtons. And there's got to be a normal force of 80, right? To cancel out the weight of the board. Make sense, you guys? All right, so all of these problems are just about creatively / strategically setting net force equal to 0 and net torque equal to 0. That's almost every one of these problems. Is might even be every one of these problems. Cool? All right. Anything else jumping out at you guys? We got a couple more minutes. How'd you guys do with 9? The picture frames there? Why is the tension the greatest in number 3? You got these 3 drawings. Sorry, multiple choice number 9. This one has the biggest tension if all 3 pictures have the same mass. Say it again? Good, yeah. So the idea is these 2 vertical components here have to add up to cancel out mg, right? Oops. Yeah, and you're right. Because this angle is farthest off from vertical, this tension is going to have to be very big so that these little components here add up to cancel out mg. That's like, I don't know if you guys remember a while ago, there was a problem about a tightrope walker, right? It's the exact same thing.
That's a weird bug.
And the weird bug. Oh, with his legs, yeah, same idea, yeah. Cool, you guys? All right. Okay, well, I guess I would say study, study, study. I'm around after school today, I'm around after school tomorrow, I'm around before school in the morning. Let me know how I can help you, all right?